Hello everyone, my name is Hoàng Ngô. I'm working in Chalmers University of Technology, and I'm going to present to you a work on a generalized Gaussian model for wireless communications. And it is a joy to work with Sheng Yang from Central Super Lake, France. Well, to start, in the MIMO communications, a conventional model that has been widely used assumes that the channel output is given by the product of a channel matrix, which is known, for example, by estimation, and an input factor, which is subject to a power constraint. And this is added with a noise, which is normally assumed to be Gaussian. This model well captures the broadcast and superposition nature of the wireless medium. It is also analytically tractable. However, in the context of emerging communication system, does this stuff fit? Well, here we provide some examples where this conventional model fails to capture the channel's characteristics. The first example is when we have multiplicative noise, such as in a non-coherent resonant channel. So in this case, the channel matrix does not only contain a deterministic part, but also a part which is random and unknown. Another example is when we have nonlinearities, such as in a phase noise channel. So in this case, we have some random and unknown phase perturbation terms from both the transmitting side and the receiver side. And these are multiplied with the channel. Well, there are many other examples, such as channels with hardware impairments, or with a channel exception error, or with quantization noise. So a question is how to treat these channels in a unified manner. Well, in our paper, we proposed a method to do so. So let's say we want to characterize a memoryless MIMO channel with a real-valued input vector of length m and real-valued output vector of length n. And the channel model is unknown. So here we propose to parameterize the likelihood function as a Gaussian PDF with both the mean and the covariance matrix being functions of the input. Here, theta is a hidden parameter that characterizes the channel. The output mean is 0 if the input mean is 0, if the input signal is 0. And the covariance matrix is given by the sum of the two parts. The first part is the covariance matrix of the term in the noise that is independent of the input. And the other part is the covariance matrix of another part in the noise that is dependent of the input. So the model is characterized by the mean function mu, the matrix W, and the matrix P. So we call this a generalized Gaussian model. Well, equivalently, the channel output is the mean plus the noise term that is dependent of the input and another noise term which is independent of the input. So here's some special cases. Well, the conventional Gaussian model is a special case of this generalized Gaussian model if we let the mean to be the product between the channel matrix and the input, and we assume that there is no input-dependent noise. The non-coherent resonant channel is also a special case. So the mean of the output is given by the product of the deterministic part of the channel matrix and the input, and the random and unknown part of the channel matrix will constitute a noise which is dependent of the input. Well, actually, the phase noise channel can be also characterized with this model, but we will address this channel later. Now we put an emphasis on a submodel of the generalized Gaussian model, which is called a linear self-interference model, where both the mean mu and the matrix W are linear functions in the input X. So the mean mu is given by the products of a given matrix A and the input. The matrix W is given by the connector product of an identity matrix and the transpose of the input. And this is multiplied with the matrix C. So in this case, the model is characterized by three matrices, the A, the B, and the C. Well, a related work. Recently, we have found that this generalized Gaussian model has been considered in this previous work. This model is considered under the name of conditionally Gaussian channels, and the authors focus on the bounded input assumptions, such as when we have a maximum power constraint, and they focus on the problem of characterizing the capacity achieving distribution. However, there are still some open questions that have not been answered in that work. First of all, how to fit an arbitrary memoryless channel to this model. Second, how to detect the signal given that we are communicating through a channel that follows this model. And third, and how to find numerically evaluable bounds on the channel capacity. So in our work, we aim to answer these questions. Now let's go to the first problem of model identification. Well, motivated by data-driven communications, we are given sequences of T-channel input vectors and the corresponding output vectors. We want to fit the underlying channel with a generalized Gaussian model. And to do so, we maximize the likelihood of the output sequence given the input sequence in order to search for the best hidden parameter theta. And since the channel is memoryless, we can write that likelihood function by the product of the likelihood function computed at each data point. Well, this maximization can be written as a minimization of the sum of the minus log likelihood at each data point. Well, the problem is this minimization is non-convex in general. So we propose the following method to solve it. We first assume that the mean and the covariance matrix can be described by a different set of parameters, theta 1 and theta 2. So in the first step, we initialize these parameters with least square. We first find theta 1 such that the mean at theta 1 it best fits the sample mean. And then given that theta 1, we find theta 2 such that the covariance matrix at theta 2 best fits the sample covariance matrix. The second step, we refine these estimates using gradient descent via alternating optimization. So we iterate between fixing theta 1, optimize theta 2, and fixing theta 2, optimize theta 1. So this model identification is a generalized Gaussian, generalization of the channel estimation step. But here we estimate the channel model, and this estimate can be refined as the communication goes on. Now we go to the second problem, which is signal detection. So the question is, given that we are communicating through a channel that follows a generalized Gaussian model, how to detect the transmitted symbol X from the output vector Y. And here we assume that the X is taken from, is uniformly distributed in a discrete finite constellation curly X. And we want to find the constellation point that minimize a given metric D. If we use ML detector, then the metric is given by the minus log of the likelihood of the output given the input. And we denote this function as F, which depends on the output, the mean, and the covariance matrix. Well, a problem with a challenge in the ML detector is that doing an exhaustive search over the constellation can be infeasible if the channel dimension is large. So in order to deal with this, we consider a version of the zero forcing that we called nonlinear zero forcing. Well, in the first step, we relax the discrete constraint on the constellation, and we minimize the ML detection matrix over the real complex real vector space. And this can be done using gradient descent. In the second step, we project the vector that we found in the first step onto the discrete alphabet X. So we find the constellation point that is closest to the vector that we found in the step 1 in the Euclidean space, Euclidean distance. And this can be done by a component-wise demapper, or we can also come up with a more clever way to do so. The next dictator that we consider is in the spirit of a linear minimum mean square arrow. So in the first step, we find a matrix F that upon multiplying with Y will give us an estimate of the transmitted signal. So this F is given by the product of the cross correlation between X and Y and the inverse of the autocorrelation of Y. And it can be computed in this way. In the second step, we are going to project the vector Fy onto the discrete alphabet X. Now the next dictator is called the self-interference whitening, and it is motivated by the fact that if we fix the covariance matrix in the ML detection metric, then the metric can be easily minimized using nearest neighbor decoding algorithms such as sphere decoding. So in the first step, we find a rough estimate of the input signal. We compute the covariance matrix with that rough estimate, and we plug this covariance matrix into the ML detection metric, and we search for the input, so for the signal that minimize that metric using the nearest neighbor decoding. And we can also iterate between the two steps. Now we get into the third problem, which is capacity analysis. So the question is to find numerically evaluable bounds on the capacity of a generalized Gaussian model. Well, if we fix an input distribution and we use optimal ML decoding, then a matched achievable rates can be found by evaluating the mutual information between X and Y. If instead of the optimal decoding, we use an arbitrary decoding metric, then we can find a mismatched achievable rate by evaluating the generalized mutual information between X and Y. So here in the expression, the likelihood function of the output given the input is replaced by e to the s times the metric that we use. So here any parameter s that is larger than 0 will give us a valid lower bound on the channel capacity. Now to find an upper bound on the capacity, we use the duality approach. So we write the mutual information as a difference between the entropy of the output and the conditional entropy of the output given the input. The entropy of the output can be evaluated by taking the mean of the minus log of the true PDF P of Y. Now, if we replace this true PDF P by an arbitrary PDF Q, then we obtain an upper bound on the mutual information. And the key here is to choose a proper auxiliary output distribution Q such that we have a tight bound. For example, in the linear self-interference model, where the matrix B is an identity matrix, we choose QY as the regularized Gaussian gamma distribution, which is given in the well-known paper of Labidos and Moser on the duality approach. And with that, we obtain this upper bound on the mutual information, which is an upper bound on the channel capacity. So to evaluate this bound, we have to compute the parameters and the functions in blue here. And here we show how to compute them using the knowledge of the matrix A, B, and C given in the model. We also have to implement several optimizations in red. So the first optimization is the infimum over the unit sphere of these parameters AI. So here AI is the I coefficient of the characteristic polynomial of the gram matrix of W. And with the W given, we can compute it, and it is a polynomial in X0. So this is a polynomial optimization which can be solved efficiently. On the outer subprimum over U can be written as the subprimum of the log of a ratio between two polynomials in U of degree R, and this can be also solved numerically. Or the final optimization over theta can be solved by analyzing the derivative of this function of alpha. Okay. Well, so we have shown three problems that we try to solve in our work. Now we will illustrate this in a specific channel, which is the MIMO phase noise channel. We assume that we have a anti times NR MIMO channel with receiver side phase noise. We assume that the received signal at antenna J is the filter signal of the product between the channel vector and the input signal in a simple period, and this is filtered with a noise, with a phase noise over the whole simple period. We assume that the phase noise is Wagner, so the phase noise follows a Gaussian distribution with increasing variance. We assume that the bus state of the phase noise in the previous simple period is tracked perfectly, so we are left to deal with the innovation part, which is the phase noise that is accumulated in the current simple period. We assume that the channel matrix follows a line of sight model with antenna spacing equal to a fraction of the optimal antenna spacing. We consider QAM input signal. So the first problem, model identification, we consider a size of case and the phase noise standard deviation is 3 degrees. We fit the channel to a generalized Gaussian model using 1,000 replicas of 100 different input-output vectors. So here we show the likelihood level set, which is the set of the output symbols such that the log likelihood of that symbol given an input symbol is equal to a given value LL. So the solid black line is the actual likelihood level set computed with the true PDF of the channel. The dashed red line is the approximate level set computed with the identifying model. And we see that the two sets are almost on top of each other, so they match very well. And this shows that we can use our generalized Gaussian model to characterize this channel very well. For the second problem, signal detection. For this, we consider a 4x4 MIMO channel, where and the phase noise standard deviation is 2 degrees. We assume 256 QAM transmission. And here we plot the vector error rate for just the SNR for antenna spacing equal to 0.7 of the optimal value, or with the optimal antenna spacing. So first of all, we plot the performance of a mismatched ML detector that ignores the phase noise. So we see that the vector error rate is quite high. If we use a mismatch zero forcing that also ignores the phase noise, then we get a worse performance, especially if the antenna spacing is small. Now, if we use LMMC with the identifying model, then we get a similar performance to the mismatch zero forcing. The nonlinear zero forcing can improve the performance, especially if the antenna spacing is optimal. Now, the self-interference whitening detectors has a much lower error rate than all the previous schemes. And to see how far it is from the optimal performance, here we plot also a lower bound on the ML performance. So this is obtained by comparing the likelihood for the output of the SIW detector and the likelihood of the actually transmitted input. So if the likelihood of the detected vector from the self-interference whitening detector is higher than the likelihood of the input vector, then for sure the ML detector would make an error, and we count an error for the ML. So here we see that the gap between the lower bound on ML and the self-interference whitening detector is not so large. Finally, we show the achievable rate of of a 4x4 MIMO channel with phase noise standard deviation 4 degree, and we consider 16 QAM transmission. We plot the achievable rate versus the SNR, and we consider two values of the antenna spacing, either 0.33 the optimal value or 0.7 the optimal antenna spacing. So we see that the mismatched zero forcing and the mismatched ML achieve a lower rate than the other schemes, that they can saturate at a lower value than the limit. Well, the SIW detector operated on the identified model achieves similarly almost the same rate as the ML detector operated on either the identified model or the exact model. And here we note that the rate achieved with ML on the exact model is the maximal achievable rate of the system given this input distribution. So we see that with the ISIW detector and using the generalized Gaussian model, we achieve a near optimal data rate. So finally, some takeaway messages. Well, we propose to use the generalized Gaussian model to characterize a MIMO channel where the conditional probability is a Gaussian BDF with both the mean and covariance matrix being functions of the input. In particular, we consider a special case where the mean is a linear function of the input and the covariance matrix is a quadratic function of the input. We investigate three problems: the model identification, the signal detection, and capacity analysis. For some future directions are as follows. So we can consider more involved functional dependence of the mean and the covariance matrix on the input. We can also try to improve the performance of the signal detectors while maintaining a low complexity. We can also try to improve the capacity bounds. So this is the end of my talk. Thank you for your attention.